Alright, welcome to the video series on chemical equations and reactions. This section is going to go back into math, and that math is going to include our dimensional analysis and the mole. So I just kind of want to do a quick little basic review over those things. I know it's been a little bit since we've done it. Okay, we need to be able to convert mass into moles, and by mass we are definitely talking about grams there. And moles to molecules, atoms, or particles. And remember, if you have to do molecules, atoms, or particles, you're going to use Avogadro's number. So here are our conversion factors down here. 1 mole of any element or compound is equal to Avogadro's number of atoms, molecules, and we need to add particles into that. And 1 mole of any element or compound is also equal to the molar mass in grams of that element or compound. So any time that you see grams anywhere, you know that you're going to need the molar mass. And where are you going to get the molar mass from? The periodic table. And if you see atoms, particles, or molecules, then you need to remember to use Avogadro's number. Okay? So let's go back through our dimensional analysis. Remember, you're going to put the given over 1 and then line up your units so that they cancel out top and bottom. So here's a little practice question. If you're given 12.011 grams of carbon, how many atoms of carbon do you have? Okay, so we just saw the word grams, which is a mass, and that means that we're going to have to use the periodic table. And we just saw the word atoms, which means you're going to have to use Avogadro's number. Alright, so we're going to put the given over 1, and then we're going to use our conversion factors. Okay, so since we have grams here, we're going to have to use the periodic table. I've got grams of carbon on top, which means I had to have grams of carbon on bottom. Okay, now where do we come up with our grams of carbon? From the periodic table. This is the molar mass of carbon. So if we look at our periodic table, then you can see right here carbon is 12.011, and that will equal 1 mole of carbon. So if you have moles of carbon on top, you have to have moles of carbon on bottom. And when you ask yourself how many moles of carbon, the answer to that question is always 1. If you're ever asking yourself how many moles, the answer is 1. Here's why. Our conversion factor up here says that 1 mole is equal to this stuff. So the answer is always going to be 1 mole because that's what's in our conversion factor. So 1 mole of carbon is equal to Avogadro's number of atoms of carbon. Okay, now we're just simply going to multiply across the top and divide along the bottom. So take a second and do that. So we get 6.0250 times 10 to the 23rd atoms of carbon. Now I have already taken into account significant digits, and I'm going to assume that you know that. I don't need to keep reviewing it. If you need a review on sig figs, go back and watch the videos over those, please. Okay, so the given has 5 significant figures in it, and that means that our answer has to have 5 significant figures in it. Okay, the next one here, I've actually already placed all of the information in here. I want you to go ahead and multiply across the top and divide along the bottom. We are trying to get from 18 grams of water into molecules of water. Okay, we said the word grams and we said the word molecules. So you figure out what that means. Okay, so if you go through here, we can figure out what the molar mass of water is from the periodic table. So we have 2 hydrogens and 1 oxygen. So you're going to add the molar masses of each of those together, and you're going to get around 18. Now, when you do your math, yes, you need to be specific and precise down here. I think it's like 18.0152 or something like that. So that's what you would need to have down here. that's going to equal 1 mole of water, and then we know that 1 mole of water is equal to Avogadro's number of molecules of water. So we ended up in the unit that they asked us for, which lets us know that we're done. So you multiply across the top, divide along the bottom. Now, what's cool for us is that 18 can cancel with 18, alright? And then 1s cancel with 1, so the answer just has to be Avogadro's number. Of course, we have to report it to the correct number of sig figs. We had 2 in the given, which means you can only have 2 in the final answer. Okay, so here's a couple more questions. If we start with 3.5 moles of sodium chloride, and since we just finished nomenclature, you should definitely be able to come up with the formula for that. How many grams do you have? Alright, we see the word grams, so that should clue us in that we're going to have to use the periodic table. Alright, let's answer this question. The first thing we want to do is put our given over 1. Okay? Since we have moles of sodium chloride on top, then you have to have moles of sodium chloride on bottom. Okay, but how many moles go on bottom? Remember, the answer to that question is always 1. Okay, so what does 1 mole of NaCl equal? Okay, well, it can either equal the molar mass in grams of NaCl, or it can equal Avogadro's number of atoms, particles, or molecules of NaCl. Since we're being asked for grams, we should probably do the molar mass, and we're going to get that from the periodic table. Okay, so we have 1 sodium and we have 1 chlorine. If we look, the sodium has a molar mass of 22.98977, and the chlorine has a molar mass of 35.453. That gives us a total of 58.43 grams of NaCl. Now we need to multiply across the top and divide along the bottom. That gives us 204.505 grams of NaCl. Now we need to take care of sig figs. We're only supposed to have 2, so the first significant digit is here, the second one is here. The third one does not round this up, so that means our final answer is 2.0 times 10 to the second grams of NaCl. Why is it not just 200? Well, because there's no decimal point here, which means there's only 1 sig fig in this number. So the only way to write 200 with 2 sig figs is through scientific notation. Alright, I want you to take a second and see if you can answer this one on your own. Okay, here's what we've come up with. I put the given over 1. Since we have molecules of silver nitrate on top, you have to have molecules of silver nitrate on bottom. Anytime you see atoms, particles, or molecules, you use Avogadro's number. Avogadro's number is equal to the molar mass in grams of any compound or element. We have a compound here, which means it had to be broken down. So we went and got the molar mass for silver, the molar mass for nitrogen, and the molar mass of 3 oxygens, and added them all up to get this number here. Then we multiply across the top and divide along the bottom. You'll see that 6.02 times 10 to the 23rd cancels out on top and bottom and leaves us with this number here. However, we can only write it with 3 sig figs since that's what our given has. So 1, 6, and 9 are the first 3 significant digits. The 8, though, will round the 9 up to a 0 and the 6 to a 7. However, if you write 170 without this decimal point here, it only has 2 significant digits. So you have to make sure to include that decimal point. Or you can do it in scientific notation by moving the decimal place over by 2. So you could say 1.70, so that you have your 3 sig figs, times 10 to the second. And then of course you have your unit, grams of silver nitrate. Hopefully you got the same thing. Okay, let's run through some vocabulary pretty quickly. What is a chemical reaction? This is the process by which one or more substances can be changed into one or more different substances. Reactants are the original substances, and they're on the left-hand side of what we call a reaction arrow. products are the newly formed substances, and they're found on the right-hand side of a reaction arrow. A chemical equation is a way that we represent a chemical reaction on paper, and it has to be balanced because of the law of conservation of matter, which says that matter or mass cannot be created or destroyed. And so we have to make sure that they agree on both sides of the equation. So if we add up the mass of all of the reactants, it has to equal the mass of all of the products in order to obey this law of conservation of matter. Here's some more information about a chemical equation. All of the subscripts are the small numbers that are going to indicate how many of a specific element we have. And you should already know that from our nomenclature section. Coefficients are going to be large numbers in front of the chemical formulas, and they're going to represent the number of molecules of a specific substance that we have. Sometimes we're going to need to know what the formula mass is. This is just the same thing as breaking it down. Whenever you break it down and you're finding the molar mass of a substance, that could also be called the formula mass of a substance. So we just did that a little bit with our dimensional analysis practice. Here's one more. Let's say that we wanted to figure out how many grams of hydrogen there are in 1 mole of water. Well, in 1 mole of water, we have 2 moles of hydrogen. So let's see how many grams of hydrogen that is. Okay, so we have 1 mole of hydrogen on bottom is equal to the molar mass of hydrogen in grams on top, and we multiply across the top, divide along the bottom. Since we only have one significant digit in the given, we can only have one significant digit in the answer, so we come up with 2 grams of hydrogen. Easy enough, and we could do that for multiple elements in a large or small compound. Let's do a little bit more practice. Let's find the formula mass for this molecule right here, and just as an added bonus, see if you can name that. Okay, so here we've broken it down. We have hydrogen, sulfur, and oxygen in this compound. We have 2 hydrogens, and each of them are 1.00794 grams per mole. We have 1 sulfur, which is 32.06 grams per mole. And we have 4 oxygens, which are 15.9994 grams per mole. Multiplying all this stuff through and then adding it all together, we get 98.07348 grams per mole of sulfuric acid. So hopefully you came up with the correct formula mass or molar mass, and hopefully you got that bonus right by getting the name correct. Okay, so let's see if you can do this one now. Okay, so we've again broken this down. The 2 on the outside multiplies everything inside the parentheses by 2. So we've got 40.08 for calcium, 2 times 14.0067 for nitrogen. There are 6 oxygens, so we do 6 times 15.9994. Add it all up, and we get 164.0898 grams per mole of, can you name that? Hopefully you can. This is calcium, and that's nitrate, so calcium nitrate. Okay, let's talk about percent composition. This is the percent by mass of each element within a compound. It's pretty good to know the percent by mass of a particular compound because this allows us to do some other useful calculations in the future. The way that we do this is by knowing what the mass of every element is in a compound and then dividing that by the total mass of the compound. So an easy way to remember that is part over whole times 100. The part is the mass of the individual element, the whole is the mass of the entire compound, and then when we multiply by 100, we turn it into a percentage. So here's the actual formula. Percent composition equals part over whole times 100. So let's see if we can come up with the percent composition for carbon, hydrogen, and oxygen in this compound. And by the way, you should be able to name that compound right now. That's right, it's acetic acid. Okay, so let's do the first step. We need to figure out what the molar mass of the whole compound is. That's the whole in the part over whole times 100 formula. So we're going to have to break it down and add up all of the pieces. That's what this is right here. There were 2 carbons. Here's the molar mass of carbon. There are 4 hydrogens, and here's the molar mass of hydrogen. This has been rounded. You should use the one from your periodic table. And there are 2 oxygens. Here's the molar mass of oxygen. Again, that looks like it's been rounded, so you should use the one from your periodic table so that we can figure out what the mass of every individual element is, and then we'll add it all together. Okay, so we've gone through and multiplied and come up with the masses for each element and then added it all up, so we have the whole mass of the entire acetic acid formula. The next thing we need to do is divide each of the elements' molar mass by the molar mass of the entire molecule and multiply by 100. Okay, and so here's what we come up with. On percent composition, we are going to stop in the hundredths place, and then our unit is going to be the percent sign and then the element that we're talking about. If you don't have that, then unfortunately it's going to be marked wrong. So carbon is 38.01%, hydrogen is 11.36%, and oxygen is 50.63% of the acetic acid molecule. A way you can check yourself is, since this is all based on 100, all of these numbers should add up to be 100, and in fact they do. Alright, let's do one more practice problem for percent composition. Ibuprofen C13H18O2 is the active ingredient in many non-prescription pain relievers. A. What is the molar mass of ibuprofen? B. What is the percent by mass of carbon, hydrogen, and oxygen in ibuprofen? And C. What is the mass in grams of carbon in 33 grams of ibuprofen? Alright, let's take a look at letter A first. It's asking for the molar mass of the whole molecule. That's easy, we just break it down. Okay, so here we've broken down the ibuprofen molecule and we've multiplied through and added up all of the parts. So we have the molar mass, or the formula mass, of the ibuprofen molecule. So letter A is done. Letter B wants to know the percent by mass of each of the elements. So what we just found out here was the whole. Remember, the equation for percent composition is part over whole times 100. Well, we just found out what the whole is. The parts are actually these individual pieces here. So after we've multiplied each one, that would be the part that's carbon, and this one would be the part that's hydrogen, and this one will be the part that's oxygen. Let's see what that is. Okay, so here are the individual parts. Now all we have to do is put them into our formula, part over whole times 100, to get our percent mass for each element. Okay, and so here are our percent by masses, or the percent composition, for carbon, hydrogen, and oxygen in our ibuprofen molecule. Alright, so all that's left is letter C. They want to know what the mass is in grams for carbon and 33 grams of ibuprofen. There are 2 ways to go about this. We can use dimensional analysis, or we can use the percentage that we just figured out. I'm going to show you how to do it both ways. The first way we can solve this is with just regular old dimensional analysis. We take our given, 33 grams of ibuprofen, and then since we have grams of ibuprofen on top, we need grams of ibuprofen on bottom. So that's going to be the molar mass of ibuprofen. The molar mass of ibuprofen is equal to 1 mole of ibuprofen. Since you have moles of ibuprofen on top, you have to have moles of ibuprofen on bottom. We can see here that 1 mole of this entire molecule has 13 moles of carbon that make it up, or that are part of it. So we're going to use that and say that 1 mole of the ibuprofen molecule equals 13 moles of carbon inside that ibuprofen molecule. And then we have 1 mole of carbon on bottom, so that moles of carbon cancel moles of carbon, is equal to 12.011 grams of carbon. We got that from the periodic table. We multiply across the top and divide along the bottom, and this is the number that we get. We only need 2 significant digits for our answer, so that comes out to be 25 grams of carbon. Alright, let's look at the second method where we use the percent composition. Okay, so percent composition, remember, is part over whole times 100. So we're saying that no matter what the whole amount is, there will always be 75.69% carbon in that whole amount. So we're going to say 33 grams of ibuprofen times carbon's percentage here will tell us how much carbon there is in 33 grams. Now, we're dividing here by 100 because we don't want a percentage as our answer. We want to know the actual amount of grams. So we're going to divide the percentage by 100 and then multiply by 33 grams of ibuprofen. Here's the rough number that we get, and then when we take it to 2 significant digits, we get 25 grams of carbon, just like we did when we used dimensional analysis. I'm sure you'll agree this method is much easier, assuming that you already have the percent composition. If you don't have the percent composition already, then it's kind of up to you on what method you like best. Do you want to come up with the percent composition to figure it out, or do you want to do the dimensional analysis to figure it out? That's really your choice. Alright, if you have any questions over percent composition or moles, Avogadro's numbers, or dimensional analysis, please come talk to me for tutorials and I'll see what I can do to help you out. As always, thank you so much for learning with me today. Bye!